Okay, part two of week 9. What this theorem says if a sequence is a list of numbers, which is a sequence, is bounded and monotonic, then the sequence converges. And what that means when they say the sequence converges, that means that the last term, what the last term is, does it converge on a number? So we've been figuring out the last term of these things. So for instance, number 11 here, when you start like plugging numbers in, like when you start, n always starts at 1. When you start at 1, when you plug in n as 1, you get 1. When n is 2, you get a half. And then when n is 3, you get 1/3. So you can see the top number is going to be 1. So now we just have to see what the bottom number is. All right. So the limit as n goes to infinity of 1 over n, this will be 0. So you can see that what bounded means that it has a number at the top. It doesn't kind of go on forever. And then a number where it's bounded underneath, which in this case is 0. So this sequence, the numbers go between 1 and 0. So therefore it is bounded. Monotonic means, basically it means, does the sequence of numbers go up the whole time or go down the whole time? And you can see it goes from 1 to a half to a third and then to a fourth, all the way down to, in this case, to basically 0. So this one is monotonic. It goes down the whole time. Where a number like, for instance, one that to kind of show you to skip around a little bit, for instance, like like number 13. Number 13 here, when you plug in 1, you get -1. When you plug in 2, you get 1. When you plug in 3, you get -1. So this particular series, this is bounded. Okay, so it's bounded, but it goes back and forth between 1 and -1. It's not monotonic because it doesn't go down the whole time or go up the whole time. Okay, so this one is not monotonic. So if this is the case, it has to be both. It has to be bounded and monotonic, and then the last number will converge on something. So this one, you can see the last number here, it goes back and forth between 1 and -1, so it doesn't converge on anything. So the last number will diverge. There's a special case for monotonic. Number 14 here, when n is 1, so a sub 1 is 3. A sub 2, when you plug in 2, you get 3. So this one is bounded because you can see every number that we have. So this one is bounded because it's going to be 3 the whole time. So the lower bound is 3 and the upper bound is 3. So it is bounded. And a kind of a special case of monotonic. I said monotonic was, when it goes up the whole time or goes down the whole time. Another case of monotonic is if the number stays the same all the time. That is technically monotonic. So this one stays at 3. So this one is monotonic. Okay, this one is monotonic. So this last number, the a sub n, our last number, will be 3. Okay, it will be 3. So this is an example where it's bounded and monotonic. And remember, it has to be both for the last number to converge on a number. So number 14 does converge on 3. And if we go back here for number 12, this one here, when n is 1, you get 1 over 2. When n is 2, you get 2 over 3. And when you plug in 3, you get 3 over 4. So it does appear like the number is going up. And then the last number, the limit as n goes to infinity of n over n plus 1, you can see this number, the highest number here, is going to be 1, or converge on 1, I should say. So this one is bounded. It is bounded because the lowest number is a half, and the highest number is going to be 1. So this is bounded, and it is monotonic because it goes up the whole time. It goes from a half to 2/3 to 3/4, and then the next number will be a little bit smaller than 1, but it'll converge on 1. So this one is also monotonic. Okay. So that last number will converge on 1. So if it's bounded and monotonic, then the sequence or the list of numbers has to converge on a number. So the last number has to be something. Okay, so that kind of does those. 15 we'll do real quick. 15 here for that one. This one looks like it's probably going to be bounded. So let's just kind of plug in some numbers. When you plug in 1, you get 2 over 4. And then when you plug in 2, you get 4 over, plug in 2, you get 8. So we'll do one more just to kind of show you this one. When you plug in 3, you get 8 over, plug in 3. Plug in, whatever plug in 3, my bad, and you get 16. So you can see actually each one of these numbers is a half. So this one is bounded because the lowest number is a half, the highest number is a half, and it is monotonic. Remember, the kind of the special case for monotonic is if it stays the same number the whole time, that's also monotonic. Okay, so this is a half for that. Okay. All right. The next one is just the next kinds of problems are just an exercise in kind of going backwards. So here's our list of numbers. So what we want to do with our list of numbers is we want to find a formula. We want to find a sub n. What would be our formula to get this? So you can see the top is all a function, and n starts at 1, by the way. So n starts at 1. So all of the top numbers are a function of 2, or a replication of 2. So like 2 to the first is 2, 2 to the second is 4, so that'll give you that one. And then the last time, how you write the odd numbers when n is 1, the way you do that one is you do 2n minus 1, and that'll give you all the odd numbers for that one, okay? So that's how you write that formula. So just kind of plug in a couple numbers and make sure you got the bottoms here. So when n is 1, you get 2 minus 1, which is 1. When n is 2, you get 3. When n is 3, you get 5. So this one kind of works out there. So this is just kind of an exercise in that. Not really that crucial, but just so you kind of get used to this. What you'll notice in number 17 is this is called an alternating series. So the alternating series here. So this one's what's called an alternating series. This one you can see goes from minus to plus to minus. So the way you do an alternating series is you put the negative 1 here, and then since the first number is negative, you're just going to put it to the n power, because when n is 1, you get negative 1 here. So that takes care of all of these. Now the way you do the top is a little bit harder, so we'll worry about the other part of the top in a minute. The bottom is the easiest, and once you've seen this, you probably won't forget it. This is a factorial here. This is what's called n factorial. So 1 factorial is 1, 2 factorial is 2 times 1, which is 2, 3 factorial is 3 times 2 times 1, which is 6. So all of these numbers are factorial. The way you get the bottom is a little bit harder. What you're going to do is you're going to do a 3 to an n power. So that gives you 3, for instance, if n is 1. And then the way you get 2 is you subtract 1. And then the way you get the 8, if you notice that when n is 2, you get 3 squared, which is 9, minus 1, which is 8. So that's how you do that one. So that one is kind of a multiple of 3 a little bit when you subtract 1. So these are the general ways that you find a formula for the sequence. You're kind of going backwards here. So if you kind of want to stop this and kind of do some other ones, you can along the way. The easiest one is probably number 19, so we'll kind of do that one right now. So this one, a sub n, so when n is 1, you can see it's 1. When n is 2, it's 2. So the top is just n. And the bottom, it goes 2, 3, 4, 5, 6. So the way you do that one is just literally n plus 1. So when n is 1, you get 2. When n is 2, you get 3. So that's that one. For number 18, to kind of go backwards there, this one, it might be helpful to kind of write this one a little differently. See the 1 there? And then you can see this goes 3, 4, 5, 6. So the way I'm going to write 1 is I'm actually going to write it as 2 over 2. So sometimes it might be helpful to write, these a little differently, and then you'll have an easier time of getting the answer. So it looks like the top here is going to be n plus 1, because when you sub in 1, you get 2. When you sub in 2, you get 3. And then on the bottom, you have 2, 8, 18, and 32. So that's a little bit different also. So this one, you notice you can actually pull a 2 out of here. And when you do that, when you pull a 2 out of here, you actually get a 1, a 4. And then when you pull a 2 out of 18, you actually get a 9. And when you pull a 2 out of 32, you get 16. These are all perfect squares. So that's how you get n squared there. Sometimes there might be a different way to write this formula, which might be the same, but this is probably the best way. So if you pull a 2 out of here, you get a 1, a 4, a 9, a 16, and all these are perfect squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9. So that's how you write that one. All right. So that's kind of just going backwards on how you, if you're given a list of numbers, how you figure out the sequence formula. All right. Oh, there's a couple more here, so you can try those if you want to stop the video. All right, so this one looks like a factorial again on top. 1, 2, 6, 24, that. And the bottom is a function of 2, so 2 to the n probably. And that one looks like it works out. The bottom, 21, the last one there. This one, the top numbers are all functions of 3. So you get 3 to the n. And then over on the bottom is another factorial, just to kind of get you used to the factorials. And you're all done there. All right. Okay. So now what we're going to do is talk about a series that is actually pretty important. This is called a geometric series. So a geometric series has this form right here, either one of these forms. Okay. Now, if you notice, we're talking about a series now. So this is a little different. So a sequence is a list of numbers. So that's what it says here. A sequence is a list of numbers. And what a series is we're going to just take these list of numbers and we're just going to add them all together. So that's what the summation means. The summation means we're going to add all these together. So the bottom number here, like n equals 1, it usually is, but it can be n equals 0. So either one of these would in this type of form, and I'll show you down here the kind of form that you're going to need to see. And it all depends on this number here, this r value. If the absolute value of r is less than 1, that means this converges, and this sum will converge to this little formula there, a over 1 minus r. If r is greater than 1, or the absolute value of r is greater than 1, then it's going to diverge. Then that series won't add up to anything. So that's what we're going to do now, is take these lists of numbers and see if they add to anything. Okay. So what we're going to do also is kind of rewrite these a little bit to kind of show you how it fits the form. So this one you can see starts at 1. And what we're going to do is kind of make this a little bit nicer. All right. So this 3 is going to come out front. That's like our A. A is a number. And then what the R pertains to is a number that has the exponent to it. Okay. So since we took the 3 out, we actually have this. We actually have 1/2 to the n minus 1. All right. Because even when you have 1 to whatever power, it's still 1. So when n is 1, you get 0. 1 to the 0 is still 1. So what we're going to do is focus on this number. This is our r. Our r is 1/2. So when r is 1/2, remember, you go back to what r is. So as long as this number basically is less than 1 or greater than -1, this is going to converge. This series, this list of numbers, when we add them up, is going to converge. So that's all you have to look at when you're looking at a geometric series. So now we can say, since it converges, we can figure out what it adds to. So the formula is a over 1 minus r. All right, so a is 3. That's the number. And then r is 1/2. So it's 1 minus 1/2. So you get 3 over 1/2, which is 6. So this will converge on 6. So when you add up all of these numbers, when you start plugging in n is 1, n is 2, get those lists of numbers. And remember, this goes on forever because the top number is infinity. This will converge. Now, if r, like the next one, you can see, we'll kind of set this one up a little bit just to kind of show you. This one starts at 1 and then infinity. There's actually a number out here, 1. So a is actually 1. And then you have, this is going to be our r value here. So this is to the power. So you can see r is equal to 3/2. Then it's going to diverge. So when this series, when it diverges, that means that you would keep adding these numbers together and it would not converge on any number. You don't have to do anything else. You could just say that it's a geometric series, r is equal to 3/2, and it diverges. So all of these are geometric series right now. And that's the form you have to get used to seeing. It's a geometric series when you have an a and an r there. All right. So now I'm going to stop the video there. So now we'll get into what's called a telescoping series, which is a little bit different. So we're going to stop the video at this point.